really exciting place. I think I see a supernova on Mars, and we're rolling like the rover. Everything is so celestial, made friends with an extraterrestrial. Out here in outer space, out here in outer space.
Hey, welcome to my channel. This is where I'm going to post some astronomy videos. You know that I'm devastated that I'm not teaching you guys about star death. It's one of my absolute favorite things. I put some cool videos on there for you, but I'm still heartbroken. Aww. So what I want to do real quick in a non-ideal situation is try to talk to you guys about what happens when a neutron star forms. So these are only going to happen when a large-ish star collapses. It has to be a little bit bigger than about 2 solar masses, but not so big that it collapses into a black hole. As we saw with stellar evolution, as stars age, they start to build up heavier and heavier and heavier elements in their core until finally they fuse iron. At that point, that's the death knell for any star, because all of the energy arrows are turned back in on the core, and you have a catastrophic collapse where only the fundamental forces are standing against gravity. So let's take a look at what a supergiant star might look like right before its collapse. All right, so here we have a circle, but I need you to pretend like that circle is a star like Betelgeuse. Maybe a little bit less massive than that. So it's at the end of its life stage. It's still primarily hydrogen though. Most of this star is composed of unfused hydrogen, and most of this hydrogen will never undergo nuclear fusion. The pressure is not high enough in those outer layers of the star. So let's start peeling back and see what we see inside. So importantly, in a shell around this, you're now going to have a hydrogen to helium fusing layer. You're going to have a helium to carbon fusing layer, and so on. You guys have seen that cascade. But the important one I want to show you guys now is in the final moments of a star, in the very core itself, it'll start to fuse iron. And why is that important? How is it different than the other ones? So let's get that portion up here now. So you're going to have this iron build up in the core. So let's look at the energy arrows. We know that gravity can only do one thing. It's trying to kill the star from the moment it's born. So every arrow is pointing inwards in terms of the force of gravity. So we'll label these big G all across the board. What's keeping the star alive and inflated is the nuclear reactions going on inside. It's producing matter-antimatter annihilations, gamma radiation, and what we call that is the radiation pressure from inside the core of the star is keeping it inflated. So each one of these layers is producing some radiation pressure. The hydrogen and the helium is most ideal. The helium to carbon produces some radiation as well. But as these fuels begin to become exhausted, those radiation arrows begin to diminish, or you can think about the energy inside the star starts to die out. Now, iron doesn't just produce less energy per nucleon fused, it actually consumes energy, and that's the big problem. If we looked at it with a graph, you would see up until iron, if we imagine here, this being energy, and these being the elements, we see that hydrogen to helium fusion produces a ton of energy. This is great. This is delicious food for the star. We see that helium to carbon fusion produces a little less, and so on. But when we get to iron, iron doesn't just make less energy or no energy, it requires energy to fuse. So suddenly, all of these arrows that we're pointing out, keeping the star alive, fighting against gravity, are turned back inwards on the core. And gravity, of course, never shuts off. So at this point now, gravity's got it. And it collapses down catastrophically on the core of the star. back to what atoms are: protons, neutrons, electrons. We're going to zero in on any protons that might be in the core itself, and all the electrons that are surrounding it in that giant plasma ball cannot even withstand the pressure of gravity. So the individual electrons are jammed inside the protons. So we have a positive charge and a negative charge, and when those are forced together in a process we call electron capture, well, what do we make? Plus, minus, zero, neutral. We make a sea of neutrons. So in the final moments of this star's life, all the electrons are jammed inside as the star falls down on itself. Most of the mass of the star remains, and we have a dense core of really only neutrons, probably some other elements scattered in there, and a giant cataclysmic explosion occurs as well. So the outer layers collapse down on the star, and now the only thing stopping gravity from collapsing this directly into a black hole is something called the Pauli exclusion principle. You can basically think of it as this: no two particles in the universe may ever occupy the same space at the same time, or really the same quantum state. So the outer layers are infalling onto that star, and they run up against this boundary called the Pauli exclusion principle, and they explode explosively out in every direction. I'll draw some squiggly lines now to represent that. This is what we call a supernova. Specifically a type 1 supernova. It is in this fraction of a second that every element heavier than carbon is made. In the chaotic collisions that ensue after the moments of core collapse, all of the gold that we have in our jewelry, much of the radioactive material that you learned about in your virtual field trip, like uranium, those are made in that split second. These materials fly out across the broader galaxy, and one day will recoalesce into a giant molecular cloud, and then down into a globule, and then down into a star like our sun. And some of those gnarly, interesting space ingredients end up making things like the Earth, things like you and me. So we can thank the star for its contribution, and we have direct evidence of this in our very being, that these types of things occur. Of course, we can see it with space telescopes, but when we talk about you being stardust, this is literally true. A star gave its life away so we could rise up on this planet. That's also how we know our sun must be third or fourth generation. It couldn't have formed right after the Big Bang. There just weren't enough interesting materials around. Now, this is really simplistic. I wish I could do a better job for you guys. Hopefully things will get better moving forward. These are preliminary videos after all, and I mainly just want you to smash that subscribe button, so if I do have more content coming out, it gets better and better as we go. If you have any questions for me, send them in through the Remind, and I'll be sure to try to address those. And maybe in our next video, we'll talk more about black holes. Guys, have a wonderful afternoon, and I'll see you next time.